Hello, NDC Security. It's so great to see so many of you here. My name is Eli, and I'm here to talk to you about maths for an hour. I'm excited. I hope you're excited. So a bit about me. I studied maths at university in Cambridge in the UK, and since then I've been working in software. I've been doing all sorts of diverse things, from telecoms to biotech to analog circuit design, and I haven't really made a lot of use of my degree until now. But what I specialized in was the kind of maths that lends itself to studying crypto systems. So things like algebraic topology and finite fields I really enjoy, and that's what I specialized in my last year of undergraduate. So today I'm going to be taking you through the maths that underpins the crypto systems we use today and will be using in the future, probably. Yeah, let's get cracking. On the agenda, we have a brief, and I do mean brief, history of cryptography, very bare bones, just to set the context and bring us up to where we are today. I'm going to talk about RSA, how that works, when it was discovered, things like this. I'm going to take you through a worked example as well, talking about elliptic curve cryptography, the other very famous kind of asymmetric encryption and cryptography that we use today, and also with a worked example of that. Quantum computing, Shor's algorithm. You can't really talk about cryptography these days without talking about that, so we will cover that as well, also with a worked example of how Shor's algorithm can break RSA, which is really cool. And finally, to wrap up, we will talk about what is next in the world of cryptography. You know, where are we going next? How do we keep ourselves safe? So, a brief history of cryptography. There's loads of great articles out there, books about this topic. I'm going to really be brief. Sending secret messages. We've wanted to do this forever. We've wanted to do this, especially once we started having armies and spies. One of the first methods we came up with to do that is a Caesar cipher, which you can see on the screen here. This is essentially, you take your letters, you translate them, some number of letters along the alphabet, and the output is incomprehensible. It's garbage, right? Obviously, if you receive this message, to decrypt it, recover the original, you just reverse the operation. You know, you take that table that I've got there, flip it, and that's how you can recover the original message. Of course, anybody who actually sees this and knows how many numbers to translate it, can also how many letters along the alphabet to translate, can do the same. One way of looking at this is that for each letter, we translate it into a number, its position in the alphabet, and we perform some operation on that number and then translate back into letters. So here, the operation is just adding 6 across the board. Anybody who knows that that's the operation can apply it in reverse, recover your original message. So you need to have a shared secret between you and the person that you're sending it to, which is the number that you're using to translate your message. This is not very secure. You can break this trivially by analyzing frequency of letters in whichever natural language you are sending messages in. So, but it is technically cryptography. This is a cipher. Ciphers can get more complicated. So, for example, if you want to send the message NDC is great, you might translate it into its number format, again, positions in the alphabet, and then you would add a private key, some kind of cipher text. And this also has a numerical representation, so we can see that there, and you can see where I'm going with this, right? You add those two, you get a result out. In order to translate this back into letters, we have to have them be between 1 and 26, so we take the modulus. You know, you have numbers that can be translated back into letters, and you get an encrypted message. In order for somebody to receive this message and recover the original, they have to know what that private key was, that ciphertext. In this case, private key is not really a private key in the sort of asymmetric cryptography sense, in the sense that it is shared, whereas sort of private key we take to mean something that you would never share. But it's a secret that needs to be shared between both parties who are engaging in this encrypted communication. So, this is great, right? This lets you send encrypted messages. If somebody doesn't know the ciphertext, they can't get at them, and it's harder to break with things like frequency of letter analysis. But it requires that both parties share a secret. How do you get there in the first place? If you have an insecure channel, you can't just send a secret across and say, we're going to use this as our ciphertext, because anybody could be inspecting that, and now they can read your encrypted messages too. The problem here is one of key exchange. And there are lots of really cool key exchange mechanisms, things like Diffie-Hellman, which also has an elliptic curve variant. If you want to know more about key exchange mechanisms, you should go to Scott Helm's talk tomorrow morning, where he'll be doing a lot of in-depth stuff on that, I believe. I'm not really going to go over them too much today, but this is something you need in order to make good use of symmetric cryptography. We need something where you can send a secret and nobody else can read it. without having a secure channel to start with. This is what asymmetric cryptography does first. So that is the brief history of cryptography. Like I said, very brief, very bare bones, missed out a lot. So we come to asymmetric cryptography. Has anybody here not heard of RSA? Cool, this is a security conference, that's what I expect. So RSA crypto system, it was developed and then published in 1977 by 3 mathematicians whose initials are R, S, and A. That's where we get the name from. It was also independently discovered by a guy called Clifford Cox in the UK for GCHQ, one of our intelligence organizations there. And they sort of said, this is a curiosity. This doesn't have any practical use. And they kind of put it on ice. They classified it, and it never got used until it was published by RSA, Rivest, Shamir, and Adelman. And at the time, so Diffie and Hellman key exchange, Diffie and Hellman had published their method of key exchange, which again, I'm not going to go into much depth on, in 1976. And this had sparked a whole sort of influx of interest in cryptography as a field of research. So this is when things really started to pick up in the cryptography world, as it were. Everything up till now had basically been symmetric ciphertext, even things like the Enigma machine. They were symmetric ciphertext, very, very sophisticated, but that's what they were. And when we have asymmetric cryptography, one through line that we see underpinning all of these crypto systems is that they depend on certain mathematical problems being very, very hard to solve, or for them to be something that takes a computer a very long time to solve, unfeasibly long. And the problem that underpins RSA is the factoring problem. It's based on the idea that if you take 2 very large prime numbers, multiply them, and you take that result, it's very hard to then recover the original prime numbers from that resulting big number, even bigger number. And we can see how this works in practice. So we're going to take the very large numbers, prime numbers, 17 and 19. This is a bad example for another reason, which is that in practice, you want your prime numbers to be different by several orders of magnitude, at least. You don't want them to be very, very close together. But I'm using small numbers here so that this is sort of maths you can follow in your head. You can understand that you could do this yourself with pen and paper and time, right? So here's our n, and here are our 2 numbers. We need to set up some parameters in order to in order to publish a public key and have people send us encrypted messages. The first one we need lambda n, which is the Carmichael totient of n. You don't really need to know what this is, other than if you have any number that's co-prime to n, doesn't share any divisors, and you raise it to the power of lambda n, it will be 1 modulo n. It will have a remainder of 1 when divided by n. This is the definition of it. And we can calculate this for n very easily if we know its factorization, because the Carmichael totient is the lowest common multiple of the Carmichael totient of all of the factors of a number, and for prime numbers, that result is just the prime number minus 1. So we can just take the lowest common multiple of the factors of n minus 1 each. This is 16 and 18, and the lowest common multiple is 144. I don't expect people to be doing this maths in their head, but you can go away and verify afterwards if you like. So we have lambda n, and this is going to be useful in setting up more of our parameters. Next thing we do is we choose a public key, or half of our public key. We choose a number e. It has to be bigger than 2, and it has to be less than n, and it has to share no divisors. In theory, you can use 3, but this turns out to not be very secure for reasons we'll see later. So we pick 5, which is the next biggest number. Then we need to determine our private key. This is, we're going to call this D, and the property that it needs to satisfy is that when you multiply your private key and E from your public key together, you get a number that has a remainder of 1 when divided by lambda n. Not n itself, but lambda n. And this means that you can publish E without people being able to derive D, because they would need to know the factorization of n in order to get lambda n. Lambda n is secret and you never share it. So D is part of your private key. So we have these numbers, D times E, 29 times 5, 145. That's 1 mod 144. It's very nice, small numbers. So we have a public key, and that is the big number n, 323, and a little number E, which is 5. And we keep D secret, that's 29. We publish this. This is our public key. We put it out into the world. If you want to send me secret messages, here are the numbers that you need in order to do that. If somebody wants to send us a message, let's say they want to send us the message NDC. And here we're going to imagine this as a series of 3 distinct numbers. And we'll use the same cipher that we did earlier, where we just take the alphabetical position of the letters for the numbers. If somebody wants to send us this message, the way that they do that is they take those numbers and they raise them to the power of e, to the power of 5 in this case. And they get some big numbers out. Here we've got, a very big number, a mediumly big number, and a number that's actually smaller than n, 243. Then what they do is they take the modulus of each of those numbers with respect to n, so the remainder, when divided by the big number that's part of our public key, which they have, and we get some remainders. And this is what they transmit to us. They send us these 3 numbers. So now we have received this message from somebody, this encrypted message, and we'd like to know what it was that they said to us. The reverse operation is simply to do exactly the same thing, but using our private key rather than the part of the public key. So we raise each of those numbers to the power of 29, our secret private key that nobody else knows. Now, I did plug all these numbers into Wolfram Alpha. They are big. 243 to the 29th power is big. I haven't put them on the slides. So you'll have to take me on trust when I say that if you do this and take the modulus of n, you get the original numbers back out. And so we can translate those numbers back into the alphabet and see that somebody has sent us NDC. This is great. This allows anybody to send you secret messages without you having to talk to them directly first. The first thing that somebody sends to me can be encrypted, and I can decode it. So why does this work? Well, we've got our parameters here. And the reason this works is because of the way that lambda n is defined. Lambda n is defined as something which, if you take any number that's co-prime to n, and for very big n, composed of 2 very big prime numbers, almost everything is co-prime to n. If you raise it to that power, you get 1. That means if you raised it to the power of that plus 1, you'd get the same thing. Raising something to the power of lambda n plus 1, or 2 lambda n plus 1, or 3 lambda n plus 1, leaves it unchanged, modulo n. And this is what we're doing when somebody encrypts a message and then we decrypt it. Because what we did with D and E was we chose them so that they multiplied to something that has that remainder of 1, and will leave the message unchanged when you raise that message to the power of that number. Have I lost anyone so far? It only gets worse from here. It only gets worse from here. This is why RSA works. You can prove this quite a number of ways with first-year undergraduate maths. It's really, really cool. So this is essentially how you can see with pen and paper and a bit of Wolfram Alpha. You can see this working in practice, and it's simple and it works, and this continues to work and has worked for a very long time. It does have some limitations and drawbacks, though. So one of them is that big prime numbers are difficult to find. So if you take a really, really big number on the order of hundreds and hundreds of digits long, there are tests you can run to discover if this number is prime. And some of these tests will also output something called a primality certificate, which is essentially a proof that anyone can use to verify that a number is prime without having to do all the computation up front. It's sort of like once you've done the proof, you can give other people a shortcut. So if you say, I've discovered a new, really, really big prime number and we can use it for cryptography, other people have a way to prove that it is also prime. So this isn't an insurmountable problem. Obviously it's not, because we use this system. But it is a bit of a drawback. Large prime numbers are difficult to find, and they're quite expensive to find. If E is small enough, the number that the person who's encrypting a message has to raise their message to raise that out to the power, so a 5 in our example, if it's small enough that you have a message and you raise it to that power, and when you take the modulus, it doesn't change, if it's smaller than n, then anybody inspecting that message can go, I know 243, that's a 5th power. And look, in their public key is the number 5. If I take the 5th root of 243, I can find the original number. And they can do this, and they can find that the last letter of that message was C, because they know that we're using 5th powers in our encryption. That's part of the public key. Obviously, sometimes you'll have a remainder that happens to be a 5th power or equivalent. So this isn't always the case that somebody inspecting your traffic will be able to actually do this. But it's a reason you don't want to choose E, the part of your public key, to be too small. Small is good because it makes it efficient for people to encrypt messages to you, but too small and you end up running into this kind of vulnerability, which is why you don't pick 3 in practice. And lastly, there's something I skipped over. There's a lot of work that I elided in my example. I said, let's send NDC, and without loss of generality, we can represent this as numbers. If you do that directly, there are lots of plain text attacks that people can use to try and recover that message. Essentially, if anybody can encrypt messages to you, let's say I'm an attacker and I want to spy on the traffic and see what people are sending. If I think it's likely that somebody will send you the message NDC, I can encrypt that myself, look at what that encrypted message looks like, and keep my eye out for it in the traffic that's passing. Because I can also, myself, generate that encrypted message. This is a plain text attack, and it gets a lot more sophisticated than this. There are several properties of RSA that mean that there are lots of more sophisticated attacks that can be done. And the thing we do to combat this is we use padding functions. And these can be thought of a bit like adding salt into a hashing function. It's something you do to your message before you encrypt it, a reversible function that you do to your message before you encrypt it and send it. And then the person receiving the message can reverse that function once you decrypt the message and read your original. It's a little bit abstract to understand if you haven't seen it before, so I have an example from history. Here is a message that was sent on October the 25th, 1944, to Admiral Bull Halsey, who was an American naval admiral. This was encrypted and sent to him. And here you can see that this is the plain text of it. In pink, you've got padding, and you've got delimiters in blue, and then you've got the actual message in white. And the person decrypting this message didn't understand, but they misinterpreted the padding. They didn't notice the second delimiter, and they sent the message, they passed the message on to him, being like, where is RPT? Where is the Task Force 34? The world wonders. And the admiral receiving this interpreted that last bit, the world wonders, as this sort of passive-aggressive. Where is this? The world is wondering. And he threw a tantrum. He went and locked himself in his room for a couple of hours, and it nearly caused an incident. So padding functions, this is what they do. There we go. So I've talked a lot about taking the modulus of stuff. And here is where I want to start introducing the idea of groups. So here we've got the integers, the whole numbers from 0 upwards. And this is the integers modulo 11. You can see it. You can see where I'm going with this. It's a clock. You can add numbers together, and once you get past 11, you loop back around, right? There we go. And in maths, we have this idea of an object called a group, which is a set of elements that has a certain behavior. A group is a set of elements and some operation that combines 2 of them together. So here, we've got the set of numbers, 0 through to 10 inclusive, and the addition is our operation. How a group works is it has 4 rules that define it. You have to have an identity element. You have to have something that does nothing when you combine it with other elements, and this is 0. 0 plus 4 is 4. The identity element, which is why it's there in blue. This is the identity element of our group. You have to have inverses. So if I take any number in this set, there has to be another thing that I can add to it to get to that identity element. And here it's, 4 and 7. You add them together, you get 11, which is equivalent to 0 in the integers modulo 11. In this nice sort of circle diagram, every element is opposite its inverse horizontally, right? Because you add them together, you get 11, which is 0. Every element has to have a negative version. If you're combining them using addition, you have to have a negative version, right? Associativity. This is one that's pretty abstract to people who haven't done formal mathematical study. Essentially, it means if you're combining 3 things together, it doesn't matter which operation you do first. If I'm adding 1 plus 4 plus 2, I can add 1 plus 4 first and get 5 plus 2 is 7. Or I could do 1 plus 4 plus 2, 1 plus 6, it's still 7. This is not the same as saying that you can swap numbers around. 4 plus 2 is the same as 2 plus 4 in this group, but it's not always. That's a separate thing called commutativity, which not all groups have. This is slightly a confusing example in that regard because we're talking about real numbers that do also have this operation, do also have this property of commutativity. Commuting things, moving things, you can move things. That's what that means. But all groups have associativity, and it means it makes sense to talk about, you don't have to put these brackets in. Lastly, closure. If you've got two elements in your group and you combine them, the thing you get out also must be a member of that group, which is true here. You just loop right back around because you're taking the modulus. Once you know that a set of stuff, a set of elements, has group behavior, you start to be able to apply all sorts of really cool theory to it. Group theory is my beloved area of mathematics. I think it's the best thing ever, and it makes my brain go brrr. And you can apply all sorts of cool properties and findings and theorems if you know that something has a group behavior. So extending this. Have I lost anyone now? Ask. Okay, listen, I did say if anyone wants to take a nap, just listen to my beautiful voice. I won't be offended. Right, so we have a group. We understand what a group is. Something that a way of describing, something that comes up in elliptic curves is the idea of, so our operation we've defined here is addition, right? But we have a shorthand for if you want to add something to itself lots and lots of times. If I add 4 to itself 13 times, we call that times. We call that multiplication. So 4 plus 4 plus 4 plus 4, 13 times. We have shorthand for that because it sucks to have to write that out. But 13 isn't in the group. 13 isn't a number on this number wheel. But we can still do this thing. We can still do this operation. We can add 4 to itself 13 times, and we will end up somewhere back on this wheel. And the way we can do it is we can do this. You can take the modulus and you find out that it's 8. And if you want to do this in your head, or fact check me later. But I want to be clear that the multiplication that's happening, if we did 4 times 3, the 3 that I'm multiplying by isn't the 3 that's on that number wheel. It's shorthand for the operation that we do know about, which is addition, done 3 times. So you can multiply an element of the group in this way. You can perform the operation of combination that we know, which is addition, to the same element multiple times, and we can call that multiplication. This is a really confusing example because we're talking about numbers which do also have multiplication. It might make it a little easier to understand, oh, it's substituted some of them in with black. No, they're meant to be pretty and contrasty. Anyway, here we've changed the names of all the elements in the group. They all have the same relationship to each other, but they're not numbers anymore, they're just things. And if you add the sun and the skull and crossbones, you'll get music notes. But you can see that it now doesn't make sense to say, 13 times star as a maths thing. It has to mean you added star to itself 13 times. Have I lost anyone? We're all good. Okay, technically, this makes the structure that we're talking about a ring and not a group, but you don't actually need to know that. Yes, this concept of denoting repeated combination of elements, of its repeatedly combining an element with itself, denoting that as multiplication, is useful for understanding the group structure of elliptic curves, which underlie elliptic curve cryptography. This is the heaviest math section in the talk. There will be a point where I say, feel free to tune out for 20 slides. But so far, people seem to be enjoying. Vibe check, is it good so far? Am I going at a good pace? Wonderful. It's the first time I'm doing this talk, so I really want to make sure that I'm providing interest rather than just standing up on stage and feeling good about myself. So, elliptic curve cryptography. Elliptic curves. This is an elliptic curve. An elliptic curve is a function. It's a function described by the form y squared. It's x cubed plus ax plus b for some numbers a and b. Right? And it gives you a shape that looks something like this. They can look a little bit different depending on the a and b that you choose, essentially. And the thing that we care about is elliptic curves defined over finite fields. So what we're talking about is the numbers probably modulo some prime, like, for example, 11. So x and y that solve this equation have to lie in that group that we talked about, right? The numbers 0 to 10 inclusive. With respect to that group understanding of addition that we had, where you add numbers and they just cycle right back around to the beginning if you overflow 11. So, the curve doesn't really look like a curve. It looks like a collection of blobs, right? But we can define a group structure on this collection of blobs, just like we did with the number circle. And the group combination rule is not addition, because these are pairs of numbers, right? They're coordinates. But you can define a rule that combines them, and it looks like this. You add an identity element that's the same for every elliptic curve, and that is the point at infinity. We just say, this point exists, consider it floating off in the distance, and this is the identity element. So we say that if you wanted to combine any two elements, combining two elements gives you, so you have this line. Do I have a laser pointer? I do have a laser pointer. You have this line, and we say that adding these three things sums to the identity element, sums to 0, which is why it's usually denoted with this O, right? Which means that the sum of this thing and its inverse, which is the opposite, right? It's remember how in the circle, each element was opposite its inverse? The same is true on an elliptic curve. You have some bit that's above the x-axis and some that's below, and this is the inverse of that. You know, you can flip the y value and you get its inverse. So if you add these two together, you get the thing down here, which is the same as saying that if you add these three things, you get 0. Does that make sense? Cool. You don't really need to understand this massively. It's just we are defining the group combination rule. The same as the addition was for the number circle. This is the rule that lets us put two things together and get a third element of the set. And it's nice because you can draw pretty diagrams. Here is an elliptic curve that I found, that I designed for this talk. It does not look like a curve. It looks like a collection of blobs. And it is given by the equation x cubed plus x plus 5 is y squared, all over the field of 11 elements. So the same field given by that number circle that we looked at earlier. You have to take it on trust that these numbers satisfy that equation. I will be posting these slides, so if you want to check my maths at any point, you can definitely do that. And we're going to do a worked example of the elliptic curve digital signing algorithm. This is an encryption. It's generating a signature over a message that lets somebody who's receiving that message know that that message has not been tampered with and that it was, in fact, from you. So we have to define some parameters. Elliptic curve parameters look like this. They're a set of 6 things. And they're typically denoted by the letter T. I'm not quite sure why. We're gonna decide some based on the elliptic curve that I've just shown you. The first one is P, and this is 11 in our case. That's the prime number that gives us the field we're working over. We have to include the values that make up the function that we are using, which in our case was x cubed plus x plus 5. So A, we have 1 and 5. We have a point on this curve. So this notation here, E of f of p, means things on the curve that are also in our field. So the blobs. This means the blobs. And we choose one of those blobs, and we look at its coordinates. So we have some coordinates here. And this point is the thing that you will add to itself repeatedly. So that's why we need the multiplication shorthand. What's the word I'm looking for? Notation. You also need a number n. And what this means is how many times do you have to add g to itself before you get to infinity? So if you imagine those blobs going all the way back round, if we take a point, we add it to itself, and we get another point, because we've defined that way of combining points with the collinear, all of that. And if you did that again, and say, let's say this one multiplied to this, I don't know if that's actually true. If I took that and added it to this, where would I go next? And in this example, starting with 1 point, you cycle around all of the numbers. You cycle around all of the points, all of the elements of this group. At what number do you get to infinity? The identity element. That's what's meant by the order of G. So you have some point, you've picked some blob, and you need to know how many times do I need to combine it with itself before I get to the identity element. In our case, this will be 11, because it cycles around every element. You need to know the cofactor. In our case, this is 1. 1 is good. You want to choose 1. This isn't that important in the grand scheme of things. You want a small number here. Basically, it being 1 means that with the point I've chosen, we get everything in the whole group. We don't end up having only half of it. The subgroup that's generated by adding G to itself repeatedly is in fact the whole group. Right. Yeah, more properly, it's the orbit of G. Right, so this is the curve that we're talking about, and I will now I'll illustrate the numbers. So we've got our parameters here. P is 11. That's the prime that we're working on the field of that prime, essentially. We've got A and B. As I said, those are 1 and 5. We get those from the equation of the elliptic curve. G, I have chosen to be 0, 4. It was the first one I tried, and it worked, so that's what we're using. N is 11. And that means the cofactor is 1. So if you combine 0, 4 with itself 11 times, you get round. You circle all the way around to the top of the number circle, as it were. You get back to infinity. Right. Here is what happens when you combine 0, 4 with itself a load of times. And I wrote this out because I needed it, and I thought it would be good to actually have it in the slides. I did this all by hand, did this all with pen and paper. The equations for doing it are on Wikipedia. It makes me happy, but I'm aware that that's a really weird thing. But taken on trust, these are correct. And something that you might notice about these is that the inverses, where you flip the y number, they follow the same structure as the number circle. 4 and 7 go together to make their inverses. So you can see that this group that we've got by taking one element and adding it to itself repeatedly, actually has the same structure as the number circle, which is kind of cool. Hello.
Hi, I have a question. Difference between P and N?
The difference between P and N. So P is the characteristic of the field you're working over. It doesn't have to be the same as N. In general, they end up being, in a lot of cases, they can end up being the same. This is, the thing you want to look at is Hass's theorem of the number of elements on an elliptic curve over a finite field. P is like, what modulus are we working in? And then N should be how many elements are there, how many blobs are there? In this example, they happen to be the same. They won't always be. P isn't always a prime. You can use powers of 2, I think, as well. Or you can use powers of 2 minus 1, I think. That I didn't look very much at because I like prime numbers, so I chose to work with those. They can be different. They do not have to be the same. In this example, they are different because it's a nice, neat, friendly example. Does that help? Yeah. Cool. So this is what happens when you take this element that I've chosen to be our special element and you add it to itself a lot of times. And I'll be using these later. These will crop up essentially whenever I assert that like 7 times G is 2, 2. This is what I'm working from. So don't be afraid when we see this in the dense maths that's about to come up, because this is not yet the dense maths. Cool. So here's the dense maths. Here, I'm going to take you through the worked example with these parameters like we did with RSA. This is the point where there's about 18, 20 slides of fairly dense maths that I have no idea how easy it is to follow because I wrote it. So I'd really, if you want to check out, I'll tell you when it's time to check back in. But anyway, let's get on with it. We have to pick a random number, our private key. And it has to be a number between 1 and n minus 1. So between 1 and 10. We can't pick 0, it has to be in there. I pick 3, because why not? This can be any number, essentially. You calculate the other part of the public key, which is a point on the curve that you will publish. And this is our base point, G, which was 0, 4, added to itself 3 times, using that rule of addition that was to do with the collinear points, right? So we have a public curve point, and this is going to be published as part of our public key. This is what we publish, by the way, just the curve point, along with the curve and the field, which is 11, integers modulo 11. Now, let's say somebody we want to send a message to someone, and we want them to be able to verify that we sent it and that it wasn't tampered with. and we express it in binary. This says NDC, by the way, in case you didn't guess. What we do is we take the last few bits of it, and we take the last few bits. How many bits we take is related to how big our field is. And this is why in practice you want a really big field, because the more bits of your message you use, the more secure it is, the less likely you'll have a false positive, things like this. So bit size of our group is 4 bits long, because 11 has 4 bits in binary. So we take the last 4 bits of our message, and this is Z. And we'll convert it back into friendly decimal numbers for now. This is 3. This is what we're going to generate the signature over. Now, per signature, before we picked our numbers and those are static across, like that's our public key. Now we pick a number that changes with each signature. It should be unique to this signature. And it's another number between 1 and 10. And if you don't pick a different number every time, people can reverse engineer your private curve point and your private key. Now what we have to do with this number, remember when we picked a point E and we had to find something that multiplied with it, modulo lambda n? We do essentially the same thing here. We find the inverse of, for multiplication of that point. So we picked 5 for our number, and then we need to find out what it multiplies with to become 1 in modulo 11. This is 9 times 5 is 45, which is 1 more than 44, which is a multiple of 11. So 9 times 5 equals 1 modulo 11. This is why we do it programmatically, because it's kind of hard to do by hand. So we take that number, 5, and we multiply our base point by it, and we have those coordinates. We need those 2. And we're going to use these to create a signature. Now, we calculate the points of our signature, R and S, and you do this. R is the point that we just got by multiplying by K. You take the X value, and mod N, which is always, it will always be mod N. You take, and then for the other one, you have to take Z, which is the bit of the text that we're generating the signature over. You have to take the number you just got, the X coordinate of the point that we just got, multiply it by your private key, dpk, and then you have to multiply all of that by the inverse of K, which is something that is generated per signature. This is dense. This is all, I'm just showing you that you could do this with pen and paper in enough time. I'm not actually expecting people to necessarily follow this. This gives us R7 and S7, and this is the signature that we send. So we send our message along with these 2 points. If either R or S turn out to be 0, we have to go back and pick a different number. But this is not very common. But if it's 0, then it means that the person looking at the signature will not be able to verify it, because it's kind of like, it's like dividing by 0. They just get nothing from it. They get no information from it. Right. If I was going to receive a message from somebody that's this binary, and they send me this along with the signature, 77, and I know what their public key is, can I verify that this wasn't tampered with and it came from them? The way you do this is now we're in the position where we've received this message. We've got the signature, R7 and S7, and we know their public curve point. And that's all we know, apart from the curve that they used and the field that it was generated over. So we get the message, we get that binary message, and we can do exactly the same thing. We can take the last 3 messages, last 3 bits, because we know the field, so we know the bit size of the P that the field is, and so we can take the last 4 bits, which gives us the number 3. And we do a bunch of more parameters, essentially. We use that bit of the message, and we take the multiplicative inverse of this point, which in this case is 8, because 8 times 7 is 56, which is 1 mod 11, and we get this number here, we get 2. And we do the same here. We take the R that we got, so we're using both parts of that signature, and we multiply it by that inverse that we just calculated, and we get another number. So we've got 2 and 5 up here. And now we also have to do some elliptic curve point multiplication. We use the public curve point that they published, hang on. Yeah, we do that, and we use this as well. So that we do some, sorry, I've confused myself. We do some elliptic curve multiplication, basically. And this is the stuff that took me the really long time, is doing a lot of this by hand. Oh no, the PowerPoint. The PDF is, okay. This is because it's the PDF version. It's not my nice Google Slides version. Anyway, this is the bit where I really heavily rely on that chart of numbers that I made earlier, all of the points multiplied, you know, that cyclic structure of the group. You can basically use that to quickly do this multiplication. The nice thing about this is computers are very, very good at doing this fast. We have good algorithms for this. Anyway, we get out a point at the other end, which is this, and that's one of the blobs on the elliptic curve. If it's not, we know there's been a problem. And we take the first bit of it, the x-coordinate of it, and we see, is that the same as that? And if it is, the signature is valid. Right. I did warn you, that's maths. Cool, it's great. Anybody who checked out, now is the time to check back in. Yes, question?
You checked the message, but did you only check the last few bits of the message?
So the signature was generated over the last few bits of the message. And this is because, like in practicality, you use really big fields, so you end up with a larger chunk of the message. This is because essentially you can get it, like it sort of overflows, if that makes sense. Like if you can only do the signature over a certain size of number, as it were. I tried to find out exactly why that is, and I struggled to. I think I sort of understand it, but I don't have a good answer for you. But yes, you generate the signature over the last chunk of your message, and how big that chunk is depends on how big the prime number or the number that you're doing all of your maths modulo.
But wouldn't that mean that you could change the n to a different character, and then the signature would still match, but the message would be?
Yes, and this is why you want to use really big numbers for the characteristic of your field. Yeah, no, that is absolutely a constraint, for sure. So the question was essentially, because you're generating the signature over the last few bits of your message, doesn't that mean the first bits of your message can be tampered with and the signature still matches? And yes, that is true. Right. Show of hands, who followed that? Because I'm not intending it to be everyone. Okay, cool, good feedback, thank you. Anyway, the short of it is, elliptic curve cryptography works, elliptic curve digital signing algorithm works, and it has some analogies to RSA in that you're doing a lot of maths, you're doing a lot of modulo arithmetic, you're doing a lot of groups, you're using group theory and group structure in order to prove that these things can be, like, these things are invariant under certain operations, like multiplying by lambda n, like raising to the power lambda n in RSA. And that you can transmit information using this kind of group structure and recover it back at the other end. Right, so all is well, right? Elliptic curves, they're great. They have been superseding RSA for the last couple of decades. They've got smaller key sizes for the same security level. So the time it would take to break this, the difficulty of the problem that they rely on, the mathematical problem that they rely on, lets you have a smaller key, sort of private and public keys, which makes computation much, much faster. You have smaller payload sizes for things like signatures, which is also good because you're sending less traffic, sending less sort of volume of traffic. And they're very, very fast to compute as well, in part because you are able to have smaller key sizes. So this is great. This is why they've been overtaking RSA. It's why, everywhere you generate a new SSH key and you use ECDSA for that. So this is all roses, right? Well, it's not quite, because quantum computers. So quantum computing, the theory of it has been around for ages and ages. Shor's algorithm, the new hotness that's going to break everything and is celebrating its 30th birthday this year. So I talked earlier about asymmetric cryptography relying on certain maths problems being very, very hard to solve. RSA depends on the integer factorization problem. So if you take two big prime numbers, you multiply them, it's very hard to recover them from the result. Other ones depend, elliptic curves, and, well, specifically elliptic curves depend on the elliptic curve discrete logarithm problem. but here are two more problems that give rise to the discrete logarithm problem in particular is what makes Diffie-Hellman key exchange work. And the elliptic curve variant of it is the hard problem that makes elliptic curve cryptography secure. And these problems are hard to solve with classical computers. It's what means that your traffic is encrypted, and it would take a classical computer longer than the universe has, the heat death of the universe, in order to decrypt it. But quantum computers work differently, and Shor's algorithms, more precisely, give us ways to solve these problems. For example, Shor's order-finding algorithm tells us that for any given number n, any number, big as you like, whatever, and any number a between 1 and n, we can find the smallest number so that when you raise a to that power, you get something that's 1 more than a multiple of n, right? And we can do this in polynomial time. This might not sound like much, but this is groundbreaking. This is not something that classical computers can do. And I will show you how it breaks RSA with a small example. So let's go back to the example we used earlier, where we've got our big N, 323, which is the product of two very big prime numbers, 19 and 17. Let's pick an A, any A. Let's say 11, because we like 11. Shor's algorithm gives us, for free, computationally speaking, for free, that if we raise 11 to the power 48, it will be equal to 1 mod 323. It is 1 more than a multiple of 323. This is another one where I used Wolfram Alpha. I literally stepped through every power of 11 until I got to 1, because classical computers are not good at this. With that information, we can factor 323. We know that 11 to the 48 is 1, mod 323. If we imagine the circle, the number wheel, but with 323 instead of 11. So subtract 1 from both sides. 11 to the 48 is minus 1 is 0. And we can factor that, the difference of two squares. So we know that 323 divides that expression there, 11 to the 24 minus 1, times 11 to the 24 plus 1. And we know that 323 doesn't divide 11 to the 24 plus 1 because Shor's algorithms gives us the smallest r. 48 is the smallest number that that's true for. So we know that that's 323. Not all the factors of 323 divide the first half, that first bracket. Some of them must divide the second bracket. At least some of the factors of 323 divide this number, this big number that we have. If we know that, we can calculate the greatest common divisor of these two things. And if we know that they share some factors, well, either 323 divides this exactly, and the greatest common divisor is 323, that's at most half likely to happen. And the more factors 323 has, the less likely it is. The more likely it is you will find something that gives you a greatest common divisor, which is not 1 and is not the number itself. And as soon as you have that, you know a divisor of 323, and you can factor it. So we have now, using this information that Shor's algorithm gives us, that's very, very hard to find otherwise, we can factor big numbers. Yeah, we have now discovered, we have solved this very, very hard problem of factorization, which is great, except it breaks encryption. So we go back to the very hard problems that our modern encryption relies on, and Shor's algorithm has knocked out that one. He created more algorithms. He broke those ones too. And this is terrible, right? What are we going to do? We can't send encrypted traffic anymore. Well, what we have now is post-quantum cryptography, which is a great buzzword. So asymmetric encryption relies on hard mathematical problems. Those aren't the only hard mathematical problems there are. For example, we have something called the isogeny finding problem. An isogeny is a particular kind of mapping between two elliptic curves. That curve that we looked at, if you've got two that you can do this particular kind of mapping between, that's called an isogeny. And if you know that two curves there is a mapping that exists between two curves, but you don't know what it is, that's a very hard problem to solve, and it's not one that quantum computers are good at breaking. This gives rise to a couple of crypto systems, Psych and SIDH, which are supersingular isogeny key exchange and supersingular isogeny Diffie-Hellman. These were submitted to the National Institute of Standards and Technology, but were essentially withdrawn because they got broken pretty spectacularly by a classical computer, actually. there is a sort of extension, a variation on the supersingular isogeny Diffie-Hellman called Seaside, because it was developed, the people who developed it were near a large body of water when they developed this. So they decided that its pronunciation should be Seaside. And this is called commutative, that's that word again, commutative supersingular isogeny Diffie-Hellman. Try saying that after tonight's party. And this is cool, this is great, there's a lot of buzz about this, but I found a paper by Xavier Bontin and André Schottenlohr. And in this paper, they, in their conclusion, they basically tried to do a bunch of quantum attacks against this, this key exchange system. And they said, actually, this only seems to provide about half the quantum security that we expect. So unfortunately, as fun as its name is, this should also be considered insecure. There's another article I saw by somebody called, I think, Andrew Pikert, and he titled his, he sells C sieves by the seaside, because a C sieve, like letter C sieve, is a method for is a technique for breaking encryption algorithms. So the puns don't stop there just because the crypto system is insecure. Now this is sad that these systems based on this particular problem aren't considered secure, but they do show that there is potential for using other hard mathematical problems to give rise to crypto systems. And one that does seem to work so far is the learning with errors problem, which I won't pretend to understand the maths behind it. I can kind of describe it. It's a bit like adding noise into a certain method of encryption, and then using probability on the other end to decode the message that you get. It's really, really complicated. The maths so far has been like undergrad master's level at most. This is easily PhD. Like I need to go back to school if I want to understand this stuff. But it does give us crystals Kyber and crystals dilithium. Crystals Kyber is a key encapsulation mechanism, so I imagine Scott Helm will be talking about that tomorrow. And dilithium is for generating signatures like ECDSA is. These are cool, and you can use them today. So Google, this doesn't exist yet. Google has been implementing hardware, they've been doing the groundwork for hardware tokens, like YubiKeys, that include dilithium as a key signature, as a digital signature algorithm. The hard part of this, or one of the hard parts of this, was getting the algorithm of dilithium small enough to fit on the hardware that a hardware token has on it, and they used Rust to do that, apparently. So this is really cool. Hopefully in the future we will see hardware tokens with quantum resilient algorithms on them. You can actually have Kyber, one of the quantum resilient key exchange algorithms, as part of your TLS flow if you are on Chrome 15 or 16. I think it exists by default in 16, or like it exists on option in 16, and in 15 it's behind a feature flag. And the way that it works is you're creating a key using this, you're creating a signature using this, and half of it's generated by traditional ECDSA, and half of it's generated by this new quantum resilient thing, and you concatenate them. So both encryption screens would have to be broken in order for your key to be compromised, which is really, really cool. You can do this today. You can go into your Chrome and say, I would like to start using quantum resilient digital signing to encrypt my TLS. So it's great. The reason you want to do this, even though quantum computers don't exist today that can break ECDSA, is because storage is cheap and storing traffic is cheap. Spying on traffic, storing it on a hard drive for 20 years and encrypting it, decrypting it then is cheap, or might be cheap, depending on how expensive quantum computers are then. And traffic that is sent now might still be sensitive by that time. So encrypt your traffic today, even though it's not breakable today, because it will be. This is really, really cool. I'm a Firefox user. I can't wait for this to come to Firefox. This is really cool. If you want to know more, the Open Quantum Safe is a really cool project that's going on. It's sort of open source libraries. I am having to currently fight back the urge, the temptation to get back into writing C, where I started, in order to contribute to liboqs, which is a C library for a lot of these algorithms. It's really, really, really cool. Things I hope to see in the future for post-quantum cryptography, which hopefully will be coming soon, more diverse crypto systems. So the two that I've mentioned here, Kyber and dilithium, are both based on the learning with errors problem. There are other hard problems that may give rise to crypto systems. If it turns out that quantum computers are good at solving the learning with errors problem, these crypto systems will be broken just like ECDSA is. So we should have more of them based on more diverse hard problems, so that if some of them get broken, we can drop in replacements. Quantum resilient hardware tokens, it's just incredibly cool that those could exist. I don't know, I love hardware tokens. I think they're awesome. Having those, if you're, yeah, we should have those. They're really cool. I hope they come out soon. Wider accessibility and rollout. I want these to come to, I want dilithium to come to Firefox. I want dilithium to come to Opera and Safari and Brave and every other Edge. The more people are using these, the more normalized it is, the better it will be. Everyone's traffic will be safer. So hopefully we will see more of this in the next few years. Right, wrapping up. What have we learned? We talked about how we got here, all the way from basic ciphers where you're just shifting things along the alphabet, all the way through to a lot of elliptic curves that I will be reworking that bit of the talk. Yep, we've talked about RSA and ECDSA, how they're underpinned by hard mathematical problems, the fact that those are now solved by computers and we need to find other hard problems in order to base our crypto systems on. And we've talked about some of the state of the art of that and where I'm hoping we'll go next. That wraps me up. There is a QR code there to give me feedback. It takes you to a little feedback form, just free text entry, and that's all it is. We have 5 or so minutes for questions, if anyone has any. If anyone wants to just head out and go to the party early, obviously you can do that as well. But thank you so much for your time and attention.